test of PBS's broadcasting system. So in today's class we will be looking at changing forms specifically from the general to transformational forms. Last week we looked at how to change from transformational to general, where we FOIL and solve for y, as you see here. But what we need to be able to do is get away from transformational form. We need to go into general form of the quadratic, or in doing so, we also need to be able to get all the information from that form. So we're looking to be able to look at a general form and find out what the vertex is and find out what the roots are of the x-intercepts, for instance. So that's what we'll be doing tonight. So let's take a look at an example here. What is the vertex of the quadratic function y equals to 2x squared plus 12x minus 4? So clearly this is in general form, and in order to know the vertex, we need to be able to get it into this form. And so what we can do here is we can look at the 4 steps to changing this into transformational form. The first thing we recognize here is that the coefficient here, the coefficient of x is a 1. And so what we'll want to do is we want to make that happen. So our first step in completing the square and changing into general form is we want to divide every term by a. And so the a is the coefficient of x squared, and so we're going to do that here. But don't forget to divide every term by that a value. Instead of writing y over 2, which is acceptable, we write 1/2 y, which is traditionally how we do that. Now to move, the next step is to move the non-x term over. And so what we do here is we are subtracting 2 on the left-hand side, so we'll undo that by adding 2 to both sides. And so if I add 2 to the left or the right-hand side, I must also add it to the left-hand side. So now what we have is a quadratic that's not really in either form, but the right-hand side is almost a perfect square. Now we need it to be a perfect square so we can get it into the x minus h all squared form that the transformational form has, but it's not quite there. In fact, this x squared plus 6x really looks like this. Here you have x squared, which means this side length is x, as is this side length. So this area in here is x squared. Here you have areas of x, and the reason why that is because, again, this side length is x. It's the same as this one over here, but this side length is 1. And so 1 times x gives us this x value, and we have 6 of those. So we need this shape to be a perfect square. And of course it's not, or at least not yet. So if I take those shapes and I take half of these x's and put them underneath, as you see I've done down here, then what we have is almost a perfect square. Now I'm not going to be able to draw this perfect square, but you can see if I came across the bottom there, we'd have this perfect square. But we're missing something. In fact, we're missing these. Whoops. Oh yeah, we're missing these. There we go. And what these are 1 by 1 squares. That side length is 1, this side length is 1, this represents 1. In fact, each of these represents 1. So we didn't have a perfect square. We needed to add 9 1 by 1 squares. Okay, so this is why this is called completing the square. It literally is when we add these numbers in, or add this number in, we are completing the square. So what this means is now this is a perfect square, and it's a perfect square because that side length is x plus 3, and this side length is x plus 3, and so this is exactly x plus 3 all squared. Now the question becomes, how do we do this? So what we looked at here was we took half the coefficient of x, squared it, and added it to both sides. So here's our coefficient of x, 6. We took half of those 6's and put them down here and half up here, and that meant we had 3 by 3 squared. So you always take half the coefficient of x, square it, and then you're going to add it in because you need to complete the square. And if you add it to one side, you have to add it to the other. So this x squared plus 6x plus 9 is now a perfect square. That's why I added the 9 to both sides. I could have added 27, I could have added 2.7, I could have added a negative value. I added 9 so that this is a perfect square. And as we see down here, that right-hand side, x squared plus 6x plus 9 is equal to x plus 3 all squared. And here, as you see, I just added the 9 and the 2 to make the 11. So this almost looks like transformational form. In our third step, what we just did here, to make the right-hand side a perfect square, we took half the coefficient of x, squared it, and added it to both sides. But the left-hand side is not yet in transformational form. And so step 4 is to factor out this 1 over a. And so that's because the left-hand side needs brackets. And by factoring out this left-hand side, factoring out the 1 over a, what we can do is add in the brackets. As you see here, I rewrote this 1/2 times y, which I had, and then 1/2 times 22, which is 11, which I had. So I didn't change any values here, I just changed what they look like. It still is 1/2 y plus 11, but now it's in that transformational form. So now we can see that the vertex is -3, -22. We could not have seen that, could not have predicted that out of the general form, but by completing the square, using those 4 steps, we're able to get it in transformational form and identify the vertex. So these two forms give us the same information. Here's the general equation, general form. Here's the exact same equation in transformational form. So if I asked you what is the range of this, well, again, you couldn't necessarily answer that by looking at the general form. But now we know that from the equivalent form, we know that the vertex is -3, -22, and we see that it's not reflected as we have here. And so what happens here is that we have a range of y contained in -22 to infinity. So here's some practice of these 4 steps. I'll go over these because this is an important process to be able to do. We're now, for the first time, able to get vertex information from a general form. And of course there's going to be a shortcut to this, but we have to know how to do the transformational form, get the transformational form before we get the shortcut, of course. So maybe it's a good time to pause and try these yourselves, or maybe let me go through the first one and then pause and go on to try the other 2 yourself. So here we're asking for the vertex, and I cannot see the vertex from this form. And so what I need to do is I need to to change this into transformational. So my first step is to divide everything by a. The a value is 2. So I'm going to divide everything by a here. So I have 1/2 y equals x squared minus 4x plus 1. And so now I need to move the non-x term over. The non-x term here is this plus 1. Notice that I don't call it the c value because technically the c value is plus 2. This is plus 1, so this is the c over a value. And so I'm going to subtract this from both sides. And in doing so, I'll just have x terms on the right-hand side. And now I'm ready to complete the square. Again, if you're to consider this, what this looks like is an x squared tile. And then I would have 4 x's. I put 2 there, and I'll put 2 here. And then I need to complete the square. And so you can see here that I'm missing 1 square, 2 square, 3 square, 4 1x1 squares. I don't always have to draw this picture. In fact, I perhaps can't draw the picture. Here I could. Technically, with this negative sign, what happens is this positive x squared is shaded in and these aren't. And these are positive because it's -1 times -1. So what I need to do here, as we just did in this diagram, is I need to take half of this coefficient of x, square it, and add it to both sides. And so I'll have the 1/2 y minus 1. I'll take half the coefficient of x, that's -2. Squared is positive 4. Because you're squaring that number, it will always be a positive value that you're adding here. Okay? The reason why we added that is because now this right-hand side is a perfect square. It is x minus 2 all squared. What happens here is that, and you can always know what this is going to be because it's always going to be x and then half the coefficient of x. So I see that this was a minus or a -4x. This will be an x minus 2 all squared. And over here I have 1/2 y minus 3. So the right-hand side looks like transformational form, but the left-hand side does not. So I need to factor out this 1 over a. What I can do here, I can always take this term, in our case it's -3, and I can divide it by the 1/2. And that equals a -6. What you're doing there is you're asking, here are 3, how many times can I fit half of this into all 3 of these? And of course, you can fit half in twice into each one. So that means you can fit in a half 6 times. So what we'll have here is 1/2 bracket y minus 6 equals x minus 2 all squared. I always like to double check that I haven't messed up that factoring. I absolutely need to have 1/2 y minus 3. And so here I have 1/2 y, and then I have 1/2 times -6, which is -3. So to answer the question, the vertex is 2, 6. So here's the next question. What is the range of the function? Well, here the range is just what I need to know to find the range. So I need to know whether it's reflected, and I need to know what the y value of the vertex is. And that y value of the vertex can be found, of course, if this is in transformational form. So I'm going to divide everything by a. A is equal to -1 here. So I'm going to take and change the signs of everything. This will be -y equals x squared plus 5x minus 1. Now I'm going to move the non-x term over. So I'm going to add 1 to both sides. And now I'm ready to complete the square. Now I can't draw this out. I can't complete the square pictorially here because I always take half the coefficient of x, so that's 2.5, and square it. and add it to both sides. So those decimal places. And so 2.5 squared is 6.25, and so I'll have minus y plus 6.25 plus 1 is 7.25. And here, the right-hand side is a perfect square. It is x plus 2.5 all squared. Again, close to transformational form, but not transformational form. I need to factor out this 1 over a value, which is -1 in this case. So I'll have negative, or -1 times y minus 7.25 equals x plus 2.5 all squared. So the range, I see that's been reflected, so I know that y is contained in negative infinity, round bracket around the negative infinity, up to positive 7.25 and a square bracket there. The next question just simply says put this in transformational form. It doesn't get much more straightforward than that. And so what we again have to do is our steps here. I'm going to divide everything by a, which is 0.5. So dividing by 0.5 is the same as multiplying by 2. So I'll have 2y equals x squared minus 6x plus 2. Sorry, minus 2. And so now I'm going to add 2 to both sides to move the non-x term over. And I'm ready to take half the coefficient of x, square it, and add it to both sides. Half the coefficient of x is -3, squared is plus 9. So the reason why I did that is because the right-hand side now is a perfect square. It is x minus 3 all squared. People ask, well, where does this -6 go? Well, if you draw out x squared x minus 3 all squared, it looks like this. These filled in. And so what happens here is that this ends up being, this is your x minus 3 all squared on this side as well, of course. So that makes it the x minus 3 all squared, and there is the 6x. Okay, so that's just, I kind of call that, it's foiled into it. Now that's not proper mathematics, but it helps you to remember that this -6x is foiled inside here. When you FOIL this out, you'll end up with this. On this side here I have 2y plus 11. I'm going to factor out the a value, 1 over a value, and I always take this number, which is 11 in this case, and divide it by this number, and so here I have 5.5. And there's the transformational form of that quadratic. So of course, now that we have done that, if we could only do this to every single quadratic, we could create a shortcut. And this gets messy, but it's important to you that you recognize that this shortcut is not magic. It just came from doing exactly what we did. We just had to do it to every quadratic. So let's put the following into transformational form. That means that I'm going to, take 2 of these. I'm going to take one that we can do because it has some numbers, but that's a specific quadratic. The next one I'll do the same time to every single quadratic. And so this means that I have to use y equals ax squared plus bx plus c. So as shown there, the first step is to divide every term by a. So the equation on the left, we have a equals 3. So I'm going to divide everything by 3. And on the equation on the right, the a term is indeed an a. So I'm going to divide everything by a there. It's starting to look messy, but that's exactly what we just did to the equation on the left. Now I'm going to move the non-x term over. I'm going to add 2 to both sides here, and then with this one, the non-x term is a positive c over a. And so what I'm going to do to move that over is subtract c over a from both sides. So now that I have this, my third step, of course, is to complete the square. To take half the coefficient of x squared, add it to both sides. So in the equation on the left, half the coefficient of x is 2, squared is 4. I'm going to add that to both sides. The reason why I did that is because that makes the right-hand side a perfect square. It's x plus 2, all squared. So let's try that with this one. So first of all, the coefficient of x is b over a. Half of that is b over 2a. The reason why would be because if we took b over a and multiplied it by a half, by taking half of it, we multiplied top by top, that gives us the b, and bottom by bottom, that gives us the 2a. So we're going to take half the coefficient of x, that's b over 2a, we're going to square it and add it to both sides. Now this is looking pretty complicated. But remember, the reason why we took half the coefficient of x, squared it, and added it to both sides is apparently this is a perfect square. Now we saw that over here. That's why we added the 4. That made this a perfect square. It made it x plus 2 all squared. Here, this is, again, dealing with every quadratic, but this is equivalent to writing this as a perfect square. The perfect square of x plus b over 2a all squared. And so again, it looks nasty, but this is what we have. Now the fourth step is to factor out the 1 over a term. So here I'll just factor out that 1/3. 6 divided by 1/3 is 18. And so there's excuse me, the quadratic equation, the transformational form for our original equation. But factoring out the 1 over a on the left-hand side of this equation is going to be trickier. And in fact, we don't have to do it. We can stop here, even though we don't have it in transformational form. We can still get the information we need. So any quadratic that was in general form can now be written like this. Now this is not something you're going to memorize. I mean, look at that. What you want to recognize is that you can get the x value of the vertex. We see that the right-hand side is in transformational form, and that means, that the x value of the vertex is x equals minus b over 2a. I don't know how to find the y yet, but the x value of the vertex is x equals minus b over 2a. And so what that means is I can answer some quick questions here. Here's a equation in general form. I'm asking for the axis of symmetry, which is always the x value of the vertex. And now I can find this very quickly as long as I identify my b value and my a value. B is negative 16, a is 2, x equals minus b over 2a. This is 16 over 4. So the axis of symmetry is x equals 4. Now here's a question that's asking for the vertex, but it's asking for the y value of the vertex specifically, which we have not found yet. And so I know the x coordinate, minus b over 2a. The b value is negative 4, the a value is negative 1. This gives me an x coordinate of x equals negative 2. However, we don't know how to find the y value. So there's a very well-known math term called glading it. So you glade the x value. Now, of course, you're saying, well, I've never heard of this glade. And if you're old enough to remember, this is a great joke. But if you're not old enough to remember, you might have to YouTube these commercials. You're going to glade the x value. What you're going to do is you're going to take this x value and you're going to plug it in. There's the joke. I'll let you decide if you want to pause and go look at Glade commercials from the early 2000s. In any case, what we're going to do is we're going to take this x value and we're going to plug it in. We have an equation right here, what we started with, which is a y value finder. If you give me an x value, I can give you a y value. Well, we just found the x value with this simple equation, x equals minus b over 2a. So what we can do now is we can just plug it in. Anywhere I see an x, I'm going to plug that in to get the y value. And so here, what we do is we take this x equals negative 2, plug it in, we get y equals 11. Now you'll notice here that there's a negative sign in front of the x squared, so a equals negative 1. This means that there's been a reflection. And since there's a reflection, the graph's going to go from negative infinity to 11. So now we have a very quick way of finding the vertex. X equals minus b over 2a, plug it in. And that means that we can change these forms very quickly. Here I've asked you to graph a function defined through an equation in general form. Well, I don't know much about this. I know the y-intercept, for instance, would be 0, negative 9, but that's about it. But now that I have this shortcut, I don't have to go into transformational form by completing the square. Remember, we just completed the square on every single quadratic ever, and we found that x equals minus b over 2a gives us the x value of the vertex. And now I can plug it in and find the y value. So right away, not right away, but in a matter of moments, I now know that the vertex is negative 2, negative 21. And so with that, I can plug those into my transformational form. Remember that when you're plugging in the vertex, the sign changes. Now I need this 1 over a value. Well, remember that this is the a value. And so what I have here is a very quick transformational form. And so without completing the square or anything like that, I can very quickly get the transformational form. And now I know the vertex, and I know the vertical stretch is 3, and so I can go over 1 up 3, over 2 up 12, etc. And so here is the graph of this function. I kind of needed it to change into that function to get it, but now, I can do that very quickly now. And that means that I can get the axis of symmetry, the range, the y-intercept, the max-min value of the vertex. The max-min value is always the y value of the vertex. But we don't know these values yet. We don't know these x-intercepts, and they become very important when we start to give meaning to these functions. So this is called finding our roots, and there are a couple ways that I can ask you to do that. I can ask you to solve a quadratic. I can ask you to find the zeros of a quadratic equation, or find the x-intercepts of the parabola. And basically what I'm talking about here is solve for x. So here's an example that I'll do 3 times, 3 different ways. Find the x-intercepts of the function f of x equals x squared minus 2x minus 15. And so we were stuck before because we have this x squared and this x term, and we can't undo what's being done, but we're no longer stuck. We can now write this in transformational form. We can take this and divide everything by 1. In fact, maybe what I'll do is do this out for you. So one of the ways that we can solve this is by completing the square. And so I'll take this and divide everything by 1, which doesn't change it. So I'll add 15 to both sides. I'll take half the coefficient of x, square it, excuse me, and add it to both sides. That's a positive 2, or sorry, positive 1. Negative 2 divided by 2 is 1, negative 1, and negative 1 squared is 1. And so what I have here is y plus 16 equals x minus 1 all squared. Well, now I can solve this. I can take and undo what's being done. I can square root both sides. Now, I guess I should say that I want to find the x-intercepts, so that means y equals 0. So now I just have the root of 16 equals x minus 1. And the root of 16 has 2 answers, plus or minus 4. I'm going to add 1 to both sides. And now this has 2 equations, either x equals 5 or x equals 3. So we know how to do this, but we had to complete the square. And you can see that I've done this on the PowerPoint. So what we did was we solved for the x-intercept knowing that y equals 0. We take the square root of both sides, and that gives us these 2 equations in one. And so what we get here is the 2 x-intercepts, because what we had was positive 4 equals x minus 1, or negative 4 equals x minus 1. But transformational form is not always needed. There is a shortcut. We're trying to get away from having to go to transformational form. We no longer have to go to transformational form to find the vertex. We can do x equals minus b over 2a and plug it in to find the vertex. So there's got to be a shortcut here. Now this shortcut is, difficult to get, but once you get it, you don't have to do it again. You can just use the shortcut. So this is what we ended up with. And I think what I'll do here is type this out, or write this out. So we're trying to find the x-intercepts. So we're going to start by plugging in y equals 0. And that will get rid of this term. And so now I have negative c over a plus b over 2a all squared equals the right-hand side here. So I'm going to square this b over 2a. B squared is, well, simply b squared, and 2a all squared is 4a squared. So now I need a common denominator to add these fractions. And so what I'm going to do here is I'm going to multiply this by a form of 1. I'll multiply by 4a over 4a. That gives me negative 4ac over 4a squared plus b squared over 4a squared equals x plus b over 2a all squared. What I have, whoops, I don't have that now. We're past that. So now what I'm going to do with this form is I'm going to add these fractions. So what I'll have here is minus b, sorry, I've lost my place. But we have this form. Now I'll write the b squared first, and it's a positive. So I'll write positive b squared minus 4 ac all over 4a squared equals x plus b over 2a all squared. So I just added those fractions to simplify the right-hand side. Sorry, the left-hand side. And so now what I can do is, just like we did before, I'll undo the square by square rooting both sides. That leaves the right-hand side to be x plus b over 2a. And the left-hand side, the numerator, I don't know how to square root. But the denominator is simply the root of 4, which is 2, times the root of a squared, which is just a. And there are two answers here. Now what I'll do is subtract b squared from both, or b over 2a from both sides. And I'll solve for x. X equals minus b over 2a plus or minus the square root of b squared minus 4ac all over 2a. And what happens here is that these are already common denominators, so I can write this. And this is the quadratic root formula. This solves a quadratic equation when it's in the form ax squared plus bx plus c. Now normally that equals y, but we made the condition that y equals 0. So to solve a quadratic, we have to make one side equal 0 and then use this. And so you can see here in the PowerPoint we have this, and this gets its da because it's one of the most important equations that we'll do in this course. And so now we can try that question again. Same question, same answers, but let's get this a different way. Again, since we're dealing with the x-intercepts, y is 0, which means we have it in the form. It's very important that you recognize, and this is why we have to derive this equation, have to show you where this comes from. There is a condition here, and the condition is 0 equals ax squared plus bx plus c. If that's not met, this equation can't be used. So what we have here is 0 equals x squared minus 2x minus 15, and so our a and b and c values are clearly stated, and so we can solve this. I'll actually write this out. So a is 1, b is negative 2, and c is negative 15. So x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. And so x equals 2 plus or minus the square root of 4 plus 60 all over, well, this a value is a 1, so it's all over 2. And this means that x equals 2 plus or minus the square root of 64 all over 2. So, I'll add a page here. So what we have, x equals 2 plus or minus 8 all over 2. Now remember, when we do this, the numerator is implied to be in brackets. So it's the denominator, but there's nothing to do there. So this means that x equals 2 plus 8 over 2, which is 10 over 2, which is our answer of 5. We knew that. We're not surprised by this. Or x equals 2 minus 8, again implied to be in brackets. So that's negative 6 over 2, which is negative 3. So the two x-intercepts here, as we know, are 5, 0, or negative 3, 0. I'm going to add in another page as well, just to give you another example. Let's say that we had this equation. The question would be solve for x. And so if we have 3x plus 4 equals 2x squared minus x minus 10, we can solve this. The first condition is to make one side equal to 0. So I'm going to subtract 3x from both sides. This will give me 4 equals 2x squared minus 4x minus 10. Now I'll subtract 4 from both sides, and we get 0 equals 2x squared minus 4x minus 14. Now, interestingly enough, you can, if you want to, divide everything here by 2, but that's not necessary, and it doesn't always happen. It just so happens here that these are all divisible by 2. You'd have to remember to divide the 0 by 2, which doesn't change it, of course. I'm not going to do that. I'm just going to plug this these values into the quadratic root formula. There's my A, B, and C values. So minus B plus or minus the square root of B squared minus 4AC all over 2A. And so x equals 4 plus or minus, I'll get to that in a second, over 4. And so this square root of 16. Now I have two negatives here. I have negative 4 and negative 14. And so this is going to be a positive value. And 2 times 4 is 8. And 8 times 14 is 111. I'm sorry, 112. And so here I have x equals 4 plus or minus the square root of 128 divided by 4. And so you can leave it like that. Or you can type in the root of 128 in your calculator, and you can get that decimal value. And you can leave a couple of decimal places here. I'm not going to be too picky on the decimal places. What we see here is that x equals 4 plus or minus 11.31 all over 4. And so that would mean 15.31 divided by 4. So x would equal 3.83, let's say. Or x would equal 4 minus 11.31. And then divided by 4, which gives me negative 1.83. So there's just another example of solving an equation, a quadratic equation. We have to recognize that one side had to be equal to 0, so I just make that happen. Also notice, please, that I did not use x equals minus b over 2a. Okay? That is only when I'm using the vertex, or when I'm finding the vertex. Here I'm trying to solve for x. I'm trying to find the roots of this equation, so I'm trying to find that value of the variable that makes the equation true. And since this was a quadratic, I'm going to use the quadratic root formula to solve that. So far we've been able to put a quadratic equation in general form into transformational form and solve it that way, or by making one side equal to 0 and using the quadratic root formula. But we can also factor. Now factoring doesn't always work, and it uses the 0 property. And what the 0 property is that if you have two things multiplied together and they equal 0, then one of them has to equal 0. And so if we can get the quadratic into the form x minus r times x minus s equal to 0, then we know that one of those factors has to be 0. And so this is called factoring. Now again, it doesn't always work. But if we take our question again, solving the x-intercepts of this function, we can now factor. Now how we factor is you recognize that we're looking for this form. And so if I multiply this out, I get x squared. I'll have minus Rx minus Sx plus Rs equals 0. And I can factor in an x here, or negative x, and so I have R plus S plus Rs equal to 0. So what we see is that my B value has to be R plus S, and my C value is R times S. So in this case, I'm looking for two numbers who multiply, there's the multiplication, to give me negative 15. That's my C value. And they're going to add to give me my B value, which is negative 2. And so if I look through the factors of negative 15, I have 1 and 15. That doesn't work. I have 3 and 5. Well, 3 and 5 can add to give me negative 2 and multiply to give me negative 15 if the 5 is a negative 5. So now what I can do is I can rewrite this. Here's what I did in the PowerPoint. And that means that I can rewrite this as x minus 5 times x plus 3. And that all equals 0. So now what I can do, oh yeah, I didn't want to show you that, sorry. What I can do now is I can solve this. One of these factors has to equal 0. We'll just hide this. So either x minus 5 equals 0, or x plus 3 equals 0. And so this would mean that x equals 5. We're not surprised by this. We've had this answer before. Or x equals minus 3. And so this is factoring. Factoring doesn't always work. It's very quick if it does work. But it doesn't always work. So I'm going to make the condition that I'm only going to deal with factoring when a equals 1. And so you need two numbers to multiply to give you C and add to give you B. So here's an example, solved by factoring. So what I need is two numbers to multiply to give me negative 24 and add to give me 10. Well, those numbers are 12 and negative 2. Now please note, those aren't the answers to my question. Those are just the factors. Now, since I have this in factor form, I can write either x plus 12 equals 0 or x minus 2 equals 0. And so when I solve this, I get x equals negative 12, or I get x equals plus 2. Very quick. There's very little work to be shown. I do want you to show me this equation written out. So this is called factored form. Almost a fourth form of the quadratic. Comparing this to our general, standard, and transformational. We also have a factored form. Now, by the way, there's the equation done. There's solving this equation by completing the square. And here it is done by the quadratic root formula. And of course, you get the same answer. So here are some practice problems you can try. And you can solve those. In the first one I asked you to solve for factoring. Notice the a value is always 1. In question 2, I just asked you to find the x and y intercepts, so you can do those in any of the three ways. On the midterm and on the final, I will ask, solve this quadratic in question A, and then in question B I'll say, solve this quadratic, but use a different method than you used in question A. So you do need to know at least two of these forms. So this is a very powerful tool now. We now know how to solve a quadratic, and we know how to solve it without going to transformational form. In our next session, we'll look at quadratic word problems, which, of course, apply these formulas.